All right, so we're going to work on section 3.1, you try example 2, number 2. This question is the same as number 1. Find the absolute extrema of a function on a closed interval. So we're going to follow the exact same process as last time. We're going to start by finding the first derivative of this function. So that's going to be g prime of x. We get 2 minus, this becomes 3 times our exponent of 2/3 x to the negative 1/3. Those 3's are going to cancel out, and we've got g prime of x equal to 2 minus 2x to the negative 1/3. Now, because what we want to do is we want to find the critical numbers of this function, that means we need to take this first derivative and we need to set it equal to 0. Well, what I've found is that this is not a very convenient form to solve when we've got this set equal to 0. So my recommendation is when you've got a radical x or a rational exponent turns into a radical, so rewrite this as a radical, and then any of your negative exponents that you have, rewrite them as denominators. So I'm going to rewrite this function, g prime of x, as 2 minus 2 over the cube root of x. Okay, so now that we've got this, let's work on solving it. So we've got, I'm going to move this to the other side, so we've got 2 equal to 2 over cube root x. I'm going to multiply this cube root of x to the other side, so we've got 2 cube root of x is equal to 2. And then I'm going to divide both sides to cancel out those 2's. So we're left with the cube root of x is equal to 1, which means that x needs to be equal to 1. So this represents a critical number of our function. Now, before I move any further, I want us to recall the definition of a critical number means anywhere our first derivative is either equal to 0, which we found, but there's another type of critical number out there, a type we did not see in the last example because the last example was a polynomial. This one is not a polynomial. See my finger up there? It's not a polynomial because of this exponent. So what that means is we want to acknowledge, is there a location where this first derivative could not exist? Well, think of it in terms of just a function, right? This is a function like any other. It's just a particular type, right? But this is a function. And so we look at this as it has an x in the denominator. Well, what would make this denominator give us a value that does not exist when this is equal to 0? So we also need to consider and the other case where this is equal to 0. It doesn't necessarily mean there's a lot that's extra for us to solve. It's just remembering this case. And as we go through these, I usually find that this is the scenario that gets forgotten the most often. When does this first derivative not exist? So over here, as we're working our way through that, well, the only thing that makes this true is when x is equal to 0. So this is actually also a critical number. So as we go into the second half of this example and we want to consider the different scenarios or the different candidates, I should say, for what gives us our absolute extrema, we're including the endpoints from the original closed interval, but we're also considering 0 and 1 as possible candidates. So let's do that. Last time I wrote it out as a table. I'm not this time, just to give us a little bit of variety. So what we've got is we want to find absolute extrema. Okay, so I'm going to go in order just like I did last time. I find that helps just for organization purposes. So when x is equal to -1, that's our leftmost point that we've got. Again, I'm plugging this into the original function. So we've got g of -1, and when we plug that in, we've got 2 times -1 minus 3. I am going to rewrite this as a radical. I think it's a little bit nicer to work with in that form. just because we're trying to simplify it. So this right here becomes 1. So we're looking at what's the cube root of 1. Well, that's 1. And 2 times negative 1. I guess I could have simplified that right now, right? So we've got g of negative 1 is negative 2 minus 3. G of negative 1 is negative 5. So hang on to that. We're going to come back to it, and we're going to compare it to our other values. Okay? So on to the next. I'm going to do the same thing. My next number is x is equal to 0. So again, we want to just find g of 0. Well, 0 is a really convenient number. I'm sure you know that already. We plug that in. We've got 2 times 0 minus, that's a minus sign, 3 times 0 to the 2/3. That's just 0. I think you'll see you become grateful when zeros show up in a lot of these questions. Let me move x is equal to 1 down here. So we've got g of 1 equal to 2 times 1 minus 3 cube root of 1 squared. Well, again, 1 squared is 1. Its cube root is also 1. So we're looking at, I'm going to put this as 2 minus just 3, right? This whole thing is 1. 2 minus 3 is negative 1. Positive 1 is negative 1 right here. So we've got 3 values we're comparing so far. We've got 1 more to go. That's our other endpoint when x is equal to 3. Okay, so when x is equal to 3, we've got g of 3 is 2 times 3 minus 3 times the cube root of 3 squared. Well, 3 squared, as we know, is 9. But what you'll find, and this does happen from time to time, the cube root of 9 is not something that's very clean. So let me dig my calculator out, hopefully quickly. Guess I should have got this ahead of time. If we're looking at the cube root of 3, the cube root of 9, I go to math down here at number 4, and I'm going to throw 9 in there, and we can see you get 2.08. So this becomes 2 times 3 is 6 minus 3 times, I'm going to put an approximate value in here, 2.08, but it's useful if you keep this on your calculator. So I'm going to multiply that times 3, and I'm going to say 6 minus answer. So that g of 3 is equal to negative 0.24025. And you can add more decimal places if you need to. So, in comparing these, again, remember that our absolute maximums and minimums are referencing our output values. Amongst negative 1, negative 5, 0, and negative 0.24, which of those is our maximum? Well, I would say this one is. Right? Which of these is our minimum? Well, that would be right here. Okay? And I didn't mention this in the first video, but you do have the option of graphing this function right underneath these examples on your Canvas. I do recommend graphing them, or you can open Desmos in another window if you'd like. But you can also see on this closed interval that these two values are in fact our absolute extremum for this particular function. All right, I'll see you in just a moment for example 3.